Okay. Hi everyone. I'm Jack Haddad, an assistant professor at Technion. Today I'm replacing Dr. Shao Li, the main organizer of the webinars. And first of all, I would like to thank all of you for attending this TFTC webinars, and we are in the ISTTT 21 series. Before we start, actually, I muted you, all of you, in the end of the some comments. So in the end of the presentation, we will have some time for questions and discussion. So you can either unmute yourself, or if you would like to ask some question by writing, you have the chat box in the control panel. But be aware that you need to send the message or the question to organizers and panelists only. So you need to choose in the box, send message to organizers and panelists only, and we will see all your questions. So I'm also reminding you that the whole process is being recorded, and today we are very happy to have a great speaker and a very interesting talk. So the speaker is Dr. Femke van Wageningen-Kessels. I hope that I spell it correctly. So, Dr. Femke currently studies traffic and crowd dynamics as an independent researcher based in Muscat, Oman. After her master's degree in applied mathematics, she worked as a PhD researcher at Delft University of Technology. She defended her dissertation about a new traffic flow model and simulation models in March 2013 in cum laude. After that, she added an extra dimension to her research and started studying models and simulation methods for crowd flows as a postdoctoral researcher. Almost a year ago, Femke chose to continue her research as an independent scholar, focusing on projects that interest her most, including emerging phenomena, models, and simulation. And today, the topic of this webinar is continuum theory for pedestrian traffic flow, local route choice modeling and its implication. And we would like to welcome you, Femke, and the floor is yours.
Thank you, Jack, for this nice introduction. It's an honor to be one of the presenters in this webinar series about all papers that were presented in ISTTT last summer in Japan. I wasn't there myself, but I think it's quite exciting to be part of this. Today I will present work that I did together with Serge Hogendoorn, Winnie Dam, and Doreen Duyves, all from Delft University of Technology, and Majid Safi from the University of Melbourne. And it's about a new model for crowd flow, and we included some local route choice modeling, which leads to better modeling of self-organization. So I hope I can convince you that our model will be better in showing self-organization in this presentation. So what do we mean actually by crowd dynamics? We're talking about pedestrians, large groups of pedestrians, like for example you would see in train stations, you would see at events, religious events like the Hajj, but it could also be religious events, cultural events, music events, whatever kind of events, or demonstrations like the Umbrella Revolution in Hong Kong. So here many people gather together, and we want to do some management for this, because sometimes the infrastructure isn't used to its full capacity or unsafe situations occur. We do similar things in road traffic. So what we have done is we monitor the traffic on these big screens. Predictions can be made, and then based on these predictions, management is being done. So we would like to do similar things for crowd management. We want to monitor what's actually going on, make some sort of state estimation. We want to predict how the future will look like, maybe the next half hour or an hour, something like that. And then we want to optimize. Maybe we can think of certain measures like reducing inflows at certain entrances, or maybe we want corridors only to be used from north to south instead of from south to north, things like that. We can try all kinds of different things in our simulations, and then find the optimal control, and then apply that in order to make the event or the location, whatever it is, safer and making more efficient use of the available infrastructure. So what we need for this prediction, we are focusing on the prediction in this work, is that it is fast and accurate, because we want to do some real-time control. Usually agent-based models can be quite accurate. So what I mean with agent-based is that individual pedestrians are traced. Individual pedestrians are modeled and like in a micro simulation. Instead, what we want to do is a macroscopic approach, a continuum approach. Not always that accurate, but certainly faster. That's what we have seen in road traffic, and what we will also see in crowd dynamics. In this continuum approach, we're not looking at individual pedestrians, but we're only looking at the average density and the average speed, the average flows. In order for these models to still be accurate, we also need to have some self-organization. Certain phenomena occur in crowds, and we want our model to be able to do that as well. So we will be focusing on a continuum approach with self-organization. So what exactly do I mean with self-organization? This flock of birds, I think, is a beautiful example of self-organization. There's not really a leader, but they just fly together, interact in some way, and they reach their goal. They fly wherever they need to go. We see similar things in crowds. So here you see a busy shopping street, and here in the middle, the pedestrians walk away from the viewer or from the photographer, and on the sides they walk towards the photographer. And this is what is called lane formation. There are other types of self-organization as well. For example, in this experiment that we did at Delft University of Technology some years ago, we see diagonal striping. Some pedestrians here walk from the top to bottom, and others from right to left. And if we analyze the videos that were made, we see densities occurring like this. So dark blue means pedestrians walking from the top to bottom. Yellow means pedestrians walking from right to left. And you see different time instances. And in all cases, there are some lines from from top left to bottom right, with high densities of either one flow or the other direction. And what we also see is that these diagonal stripes are moving. So that is something that we would actually also be able to include in our model and in our simulation. And we still want it to be fast. So we can actually do that. And we will show that we can do that using a continuum model with an equilibrium speed relation. So that means that it's a kinematic wave model, some sort of two-dimensional LWR model that's well known from road traffic flow. In this model, we also include a route choice model. The route choice model has two levels. The first one is strategic or global, as we usually call it. It can, for example, be the shortest route. Pedestrians just choose to go to take the shortest route to their destination. It can also be other things, like, for example, the sunniest route or the route with the most protection from wind and rain, or the route that passes the nicest shops. Then the second level of route choice is operational or local, and that's at much shorter times and distances, and it's aiming at avoiding others. People usually don't like to be in big crowds, so don't go too close to other people. It's not the first model that includes both these levels, but previous models mostly used an iterative method. So they first solved the continuum model with the equilibrium speed relationship, then they adapted the route choice to that, then again the continuum model, the route choice, etc., until there was some sort of convergence, and then the next time step can be made. So this is a very slow process. Instead, we are doing this route choice integrated in the rest of the model, which makes our predictions much faster. There are a few other elements in our model. There is heterogeneity, because we need the pedestrians to have different destinations. We also have developed an efficient numerical solver. And in this presentation, I will also show some simulation results with self-organization. But the main contribution of this work is that we have a route choice, and especially the local route choice, how we integrated that into the continuum model. So let's start with the first version of the model. Very simple, nothing really new about this, but we will build on this in the rest of the presentation. So we have a conservation equation. It's very similar to, or it actually is a two-dimensional version of the LWR model, kinematic wave model, and it simply tells that no pedestrians enter or exit unless at the boundaries. Then there is an equilibrium speed. There's some sort of fundamental diagram. Not going to discuss the exact shape, but it says that there's some relationship between the density, so the number of pedestrians per square meter, and their speed. Because it is two-dimensional, we do not only need the absolute speed, but we also need the velocity, or the direction in which the pedestrians walk. And there the global route choice comes in. So here the gamma is the walking direction, and it is determined by the cost. The cost is some value function, and I'm going to show you a bit more about that. So the walking direction depends on a global value function, phi. And this phi tells us what is the minimum cost of reaching the destination if you are at point x at time t. So for example, the global value function could have a very simple form, namely just the distance to the destination. Like I said before, you could make this much more complicated by including whether there will be sun or rain, or whether the route is safe or not, or whether it passes nice shops, or whether you have nice views, whatever. So that's just a global value function that does not depend on the actual situation. So if we do a simulation with this model, this is what we get. So pedestrians walk from the origin on the left to the destination at the right. And what you see here are the total densities. So they all walk just from left to right. They don't move anywhere else, just left to right. And there are some discontinuities perpendicular to the walking direction. So what I mean with that is that they don't avoid others. So for example, this red strip, it's quite dense, so you would expect the pedestrians to go to the left or go to the right a bit, just to be in a less crowded area, but they don't. And in order for them to do that, we need a local term. So that's the next thing we add to our model. It's what we call the local route choice, and it tells us how the walking direction adapts to the local circumstances. The way we model it is derived from a social force model. How this derivation actually works, you can read in the paper, but it results in the avoidance of crowds and delays. So then we have some local value function, phi. Again, it tells us something about the cost of being in a crowd, and it tells us something about the cost of having a delay. Then there's also this parameter alpha that's just included to weigh the cost of being in a crowd against the cost of having a delay. After some tests, we realized that this delay function or this delay cost has some influence on the results, but not that much. So for the rest of the presentation, we will just ignore that part, and we're focusing on only the local value function, including the cost of being in a crowd. So in that case, the cost equals some parameter beta times the density. If the density is high, there's a lot of crowdedness, and you don't want to be there, so the cost is high. So that gives us the following function for the walking direction. It has the global cost, or the gradient of the global cost, the gradient of the local cost. We're using gradient because pedestrians will walk in the direction of the steepest gradient downwards. So we're talking about the cost. If the cost is high, they want to go to a location with a lower cost, and that's the steepest. Then they have to follow the steepest gradient. The denominator is just there to have a normalization, so that the walking direction always is a normalized vector. So we can do some simulations with this. First, again, the results with the global, only with the global route choice. We saw that before. And if we then include the local route choice, then we get something that's much more realistic, where pedestrians also walk a bit to the left and a bit to the right, and there's dispersion that looks much more realistic than on the left-hand side with only the global route choice. But still, I can't say that there's really any self-organization in this. We don't see the lane formation, we don't see the diagonal striping. So that's the next thing we want to include in our model, and therefore we need heterogeneity. We need to be able to distinguish between pedestrians going in one direction and pedestrians wanting to go to the other direction. So why including heterogeneity? It's because we're not all the same. There's heterogeneity in speed, people have different preferred speeds or different maximum speeds. Some pedestrians can maneuver easily, others cannot. Pedestrians have different purposes for their travel. Some really hate to be a crowd, and others may not like it, but they don't really care that much. And as I said before, what's really important in our application is differences in origin and destination. So that's why we took the multi-class approach, where each class or each group of pedestrians has a different origin and a different destination. In fact, our model is quite generic, and if you want to include other things, like differences in the avoidance of crowds or differences in preferred speeds, that can also be included in the model quite easily. But for now, we see that self-organization doesn't really need these differences. We can do it, but we can also do without, at least for now. So just to repeat, the not heterogeneous model that we had a conservation equation, one relation for the equilibrium speed, a route choice model, and a crowd avoidance relation. If we include heterogeneity, then suddenly we have multiple conservation equations, namely for each class or each group D. We use the subscript D for that. We have another conservation equation. And then the density is the class-specific density, so the number of pedestrians of that class per square meter. And also the flow is class-specific. The speed is also class-specific. So we don't use it here, but in principle, it could be that the equilibrium speed is different for each class. Here it's important to note that on the horizontal axis, we still sum over all densities. That means that the speed depends on the total number of pedestrians per square meter, and it doesn't matter who these other pedestrians are. Also, that could be an extension, but we don't really need it for now. Then, next element is again route choice, and again it's class-specific, because of course the global route choice is different because pedestrians have different destinations, but also the local route choice is different per class, and the crowd avoidance is different per class. And this is how that works. Again, if we have a non-heterogeneous model, then the cost of being at a certain location is a linear function of the density there. So if this blue dot on the left actually wants to go straight to the right, but there are a few others, then this dot will avoid the others by going slightly to the top. But if we add another class, namely the pink pedestrians, who are walking from the right to the left, then suddenly this pedestrian wants to avoid the pink pedestrians much harder. It's more important to avoid the pedestrians of the other class. So that's how we implemented this in a heterogeneous model. It actually means that people walking in a, for example, in a corridor, they don't maybe they don't want to be close to other people walking in the same direction, but they certainly don't want to be close to other people walking in another direction. So that's why in the summation, each density or each class-specific density has a different weight. And if the weight is high, it means that the group D tries hard to avoid group delta. So in this example, the cost for the group D, for the blue group, would be a summation of the class-specific density of this blue group, group D, with a quite low weight, plus the class-specific density of the pink group, the delta group, with a quite relatively high weight. So that way we can ensure that pedestrians avoid other pedestrians, and especially avoid other pedestrians with other destinations. So this gives us the following heterogeneous continuum crowd model with conservation equations, with an equilibrium speed, with a route choice, crowd avoidance. So that's all rather complete for the modeling part. But then we still need this model to be solved numerically in order to be able to do simulations and to make predictions. I'm not going into details about this because that's another full paper, but I will show you some things. So we developed a Godunov scheme for this multi-class two-dimensional model. The main challenge here is that all pedestrians may walk in all directions, and we don't know beforehand where they will go. So what we do is we split the whole domain into cells, square cells. You only see one cell here with its 4 neighbors. And we want to calculate we assume that we already know the current density and the current desired speeds and directions. And then we want to calculate the new density in this white cell in the middle. But in fact, it turns out that pedestrians could walk over each boundary in each direction, and then each class, each color, could do this differently. So if we have only 2 classes, we already have 16 different possible flows over the cell boundaries, which is quite a lot. Turns out that half of them are 0, at least, so that makes it a bit easier. But if you want to know the details, I refer you to the paper. But what we, how we did it, how we managed to solve this problem with a numerical scheme, is that we extended the minimum supply-demand scheme that's known from D'Aganzo and Lebach in the 1990s to multi-dimensions. And then we only have to calculate the demand and supply for each cell boundary for each class. So if we do some simulations with that was our next step, then we can get results and we can see whether we actually have some self-organization. So the first test case that we tried after the very simple one-directional cases is this one with crossing flows. So some pedestrians walking from the left to the right and others from the bottom to the top. And it turns out that actually we do see the diagonal striping as we had hoped. So that was already exciting. I can also show you this in a video, if it works, yes. So the blue pedestrians are walking from the left to the right, the yellow from the bottom to the top. And once they meet, they are trying to avoid each other because of these beta parameters that we saw before. But at some moment they realize that they also want to go to their destinations, so they do start sharing the space. And then now you can already see the start of some diagonal striping, and that goes grows stronger and stronger. You can see really clear blue and yellow stripes in a minute. You can also see that they are moving. They're moving from bottom left to top right, which is also something that we saw in experiments in real life. Just keep watching for a bit because it becomes more and more clear. The first time I saw this, I thought it was so fascinating. Actually, I still think it's very fascinating. I could watch it for a very long time. So this is the diagonal striping that we managed to get from our model. So let's continue with the next slide. This is just another test case with slightly different setup, but again, stripes are formed. And here you see that first nothing really special happens because the outflow equals the demand. And then after a while, the stripes start being formed, but that makes the process a bit less efficient, so the outflow decreases. But then once the stripes have formed, apparently it's very efficient again, and there are some fluctuations, but there is stability around the point where the outflow equals the demand. So this seems to be quite efficient process. So we were happy to also see this, but in some cases, if we turn up the demand, then there is the formation of diagonal stripes, but then soon it fails. There is gridlock, and the outflow decreases until almost zero. But actually, that's also what we see in reality. So a bit more about varying demands. If you take the demand very low, then nothing interesting happens. This is just the densities of one class. They walk from left to right, and that's all. There's another class walking in the other direction, and that's it. If we increase the demands a bit, then we see the formation of diagonal stripes. If we increase the demand just a bit more, there are still diagonal stripes. But then if we go up, then the stripes become big blobs, and the pedestrians clump together in big groups, and a bit later there's gridlock. So I won't claim that these phenomena occur at demands that are realistic, but this results show that our model can do both no stripe formation if the demand is low, gridlock just like in real life if the demand is very high, and some region in between there is stripe formation, there is self-organization, just as we see in real life. Maybe in real life it's not at exactly these demands, but well, that's future research. We see something similar for lane formation. So if pedestrians walk in opposite directions, so here some pedestrians walking from left to right and others walking from right to left, and we see lanes occurring. Again, it takes a while before the stripes are being formed. Then there's a reduction in efficiency, but then after a while the process becomes efficient. Again, these lanes, they move from the bottom to the top, and they keep moving. They are dynamic, but they never disappear when keeping the demand the same. When digging a bit deeper into this problem, we did that in a later paper. Actually, my colleagues did that. And then you see that lane formation also depends on the parameters in the model. So here are again the beta parameters that tell us how hard pedestrians try to avoid other pedestrians of the same group and how hard they try to avoid pedestrians of the other group. And these results show that it actually depends quite a lot on the actual settings, whether lanes occur and how these lanes look like. Again, this is something that shows that the model results depend on the parameters and that it's important to choose the parameters correctly. We don't know yet exactly what the values of these parameters should be. But qualitatively, the model does what it should do. So as a wrap-up, I have showed a continuum model for two-dimensional pedestrian flow. It has an integrated global and local route choice. Local route choice is based on avoiding other pedestrians. It includes heterogeneity because pedestrians are not all the same. In our case, we chose to only include heterogeneity for origin and destination. And the simulations that we're doing with this are quite fast and accurate also in the sense of the self-organization. We see diagonal stripes and we see lane formation. It depends a lot on the demand and on the parameters and actually also on the numerical settings, whether these diagonal stripes occur, whether the lanes occur. So that's something for future research to better understand the model and its behavior. And then another thing for future research, of course, is to look at the applications in crowd prediction and in crowd management. So before I leave you with some references and time for questions, I have another video that I thought so great. As Jack told in the introduction, in my PhD, I did one-dimensional road traffic flow. Now I've turned to a crowd flow. You see the bird going down? This is 3 dimensions. And I think it's so fascinating to watch these birds flying, and then only one of them goes down, and all of them follow, and they sit in the sea. So that's another future research direction, I think. More birds coming, they will also land. So thank you for your attention. If you want to read more about this, first version of this model was published in Physica A. Then this was published in TRC or IEEE. For the numerical simulation, we presented this at the HEART conference, but there's also a paper in progress. And there's an upcoming paper already available online about self-organization. So if you have any questions, you can ask them now, I think, or you can also email us at these addresses. Now I'm going to try to open the chat box to see if there are any questions.
Okay, thank you, Femke, very much for this interesting talk. Really very interesting. So if somebody has any question, he can either unmute himself and ask directly using his microphone, or if you would like, you can write in the box, in the chat box, and send your questions to organizers and panelists only. So meanwhile, I have actually a question. And I was wondering, because you utilize, if I understand correctly, you utilize the same equation or the same function for the optimal direction or walking direction modeling. and you added some new local some new local root choice. I was wondering if there is in the literature a different uh, oh, it's the same equation? No. Yeah, it's the same. Is it? No, it's updated, right? So you integrate directly the root choice inside the walking direction. Is that correct?
Yes, indeed. We calculate the speed, so the absolute velocity from the fundamental diagram, and then the walking direction, it depends on the global cost plus some function of the density, and that represents the crowd avoidance.
Okay, so now regarding the crowd avoidance, it depends very strongly about the parameters, as you mentioned and you show in the
Yes.
figures. But how is this sensitive? I mean, the effect of these model parameters can, can affect all the self-organization occurrence. So how much these parameters, because I cannot feel it, how much these parameters are or the model is
Yeah,
for the choosing these.
so your question is how sensitive the model or the results are to the values of the parameters.
Yes, correct.
Is that what you mean?
Yes.
Um, I think it is sensitive. What it was shown in the latest Physical A paper is that the results can differ quite a lot if you take different parameters, which is to be expected. If people really try hard to avoid others, also in reality, you would expect results to be very different than if maybe in another culture people don't really care that much about being close to each other. So yes, it's important to choose these parameters correctly, and I think it's certainly a next step to see how we can make these models and these simulations match the reality quantitatively, because I think this already shows that qualitatively we can have the self-organization that we want, but we still need quite some. We need to do more work on the quantitative aspects.
Okay, thank you. There is a question from Lakshmi. Can you read it?
Yes. Can we apply two-dimensional theory for vehicular traffic flow in heterogeneous situations in developing countries where lateral movement is also high? So the question is whether we could apply this kind of model for vehicular flow. So then I'm imagining a wide freeway with lots of different types of cars and trucks and maybe bicycles and rickshaws and maybe even pedestrians. They may be crisscrossing through each other. I think in principle you could use the same theory, but probably pedestrians, they are heterogeneous, they are all different. If you would apply this for vehicular traffic flow, then it would be even much more different. And I'm not sure whether you would manage to do that as realistically as you would want to. I'm especially thinking about the crowd avoidance. These beta parameters in crowd flow, they would all be within a similar range. But for vehicular traffic, probably much wider range. Same for equilibrium speed, would be much wider range. So I don't know. Maybe could try. From the same person, two-wheelers do crowd avoidance in Indian case. Yes, of course. I think all pedestrians or bikes or cars, they will avoid crowds. They percolate through gaps. Yes, there's this porous flow model uh, that describes this flow of especially the smaller vehicles, the two-wheelers, between the larger ones, between the cars. It could be interesting to compare whether the porous flow model would perform better than a model that you would base on these ideas for the application of the heterogeneous flow in India, for example.
Okay, thank you, Lakshmi. Is there any more questions? Femke, meanwhile, I have another question. Um,
Yes.
it is very interesting because you show this figure with four figures in one slide when you change the demand, and you end up with the gridlock. And
Yes.
before the gridlock, you have the self-organization region. So actually, what I understand from you that you can distinguish between two main regions, or at least two main regions, which are the self-organization region and then gridlock. My question would be
Yes.
how much, I mean, I believe also maybe I'm thinking that there is another region in between, which is the unstable region before gridlock. This is first question, if you believe the same. And the second thing is, can you imagine or can you think in the future how you can characterize in time and in space these regions? So this diagonal life or this space region in the gridlock, the red the red regions, or if you may say, can you
Yes.
have some idea how to characterize these, maybe numerically, the borders of this region? Because these can give you a lot of useful information in the future.
Yes, we are of course very interested in these critical transitions. So somewhere between the demand of point 1 and 0.15, there's a critical transition between nothing interesting going on and uh, diagonal striping. And we'd like to know, of course, at which demand this happens. And maybe more interesting, from the diagonal striping, which is very efficient, to gridlock, which is something we really do not want. When does that occur? One way to do it would be to do lots of simulation, but we also know that it depends quite strongly on the parameters and on the numerical settings. So there's lots of variables to play with, and you get different results every time. So I think it would be more interesting to see if we can analyze the equations mathematically, and then see if we can draw any conclusions from that, whether there are any regions of the parameters where you can expect diagonal striping, or whether you can expect gridlock, and where this transition will take place. It's certainly a very interesting question that I cannot answer right now.
Okay, future research. Okay, there any other questions? Please unmute. Yalakshmi. Okay, actually, my name is Jack Haddad. I'm replacing Shao Li, but it's okay. Uh, Actually, I have another question meanwhile, if you have time. Well, it would
Yes.
be interesting because here you introduce again another, you try to model this nice dynamic feature, but I mean, I'm wondering how do you see the future in this research area? I mean, what other key dynamic features are needed for more realistic models from your experience?
What we have been looking at is only the inner domain. So, well, I've done some work, but only very little on how pedestrians would behave near walls or at a corner. And if you want to move this one step further towards application, that would really be necessary to include walls, to include obstacles, to include corners, and to make the modeling of that, to make realistic models of that. So that's, I think that's an important step to take before it can be applied in practice.
Okay, interesting. Thank you. Is there more questions? Are there more questions?
Actually, the Physica A paper, the most recent one, it does show something about how pedestrians walk around the corner.
2016, you mean, right?
Yes.
Can you show again in your slide? Just write it down. The last slide. Yeah. Oh, okay.
So the last paper here.
Okay. Okay, so if there is no other questions, I would like to thank you again for this nice presentation and really great work. And with this, we close the session, we close the webinar for today. And I hope to see you next time with the ISTTT 21 series in the TFTC webinars. So thank you, and have a nice day or a nice evening at Oman. At Oman. So thank you very much for all of you for your attendance, and see you. Goodbye.
Thank you.
Bye bye.
Bye bye.